So, hi everyone. In this problem, we have to find the frequency of most frequent element. So, let's say we have something like 1, 2, 4, 8, and 13. And you can only increment any element by at most the amount k, right? So k is some given value, some given amount by which you can increase any element. So you can take any amount from k, and by using that you can increment any of the element. In the ideal case, when you are lucky and k is very big enough, so k is almost approaching to infinity, in that case you will you would like to have every element uh, equal to some single value, right? You can't increase 13 because 13 is the biggest number in my array, and if I increase 13, I have no benefit, uh, because I want to increase an element so that it can match some existing element. So I can increase 8 to match 13, so I can increase 8 by 5 units so that it will become equal to 13. I can increase 4 by 9 unit so that it can become equal to 13. I can increase 2 by 11. If I add 11, that will become 13, and in 1 if I add 12, it will 13, right? So this 12, this 11, this 9, this 5, I'm getting from the k. So if k is big enough, I'll increase every uh, element except the largest element, except the largest one, right? But we are not always lucky, and we don't have k as infinite always, right? It may happen that uh, the gap between last element, so let's say we have element a instead of these certain elements. Let's say we have element a, element b, element c, d and e in my array, and I'm keeping them in a sorted order, so you can assume that a is less than b, c is b is less than c, and c is less than d, and d is less than e. So it may happen that the gap between e and d is very large. The difference between e and d is very large, but the gap between c and d is not that much, and same with uh, b and a, right? So the amount that we require to convert c to d, so the amount that we require to convert c to d is not as large the amount we require to convert d to e. So we will not run out of the given quota of k, right? So it is uh, we can with a very small amount I can convert c to d and b to e, and in that it may happen that k is just equal to this gap, and we can only convert d to e but can't convert c to e and b to e, right? So we never know uh, which element we should pick and convert rest of the elements equal to that element, right? But one thing is sure, one thing we are sure, that we have to pick we have to pick one element from the given array and make or I should say try to make other elements, and of course those other elements are smaller than this element. Try to make other elements equal to this picked element through increment operation. And we have a limit on increment. We can't increment as much as we want, so we can increment so we pick through increment within some quota, and that is equal to k. So we can spend only k amount of value to make other elements equal to the given element. So what we can do, first of all, to make sure that all the elements which are less than the given element are on the one side of my array. So if I pick in my given array, if I pick any random element at index I, to make sure that all the elements which are less than this element are on the left of it, that is here, and not on the right of it. To make sure that we should sort our array. Right. So the very first step is to sort the given array. To have the lesser elements on the right side of every element. So this is step 1 of our procedure to solve this problem. Now, once I got a sorted array, let's say it is A, B, C, D, E, and F. So I'll start from the rightmost element and I'll pick F. I'll try to convert E to F, and I can choose the amount from the given k. So let's take an example. So let's say I have 1, 2, 3, 4, 5, and 6. And let's say given quota is of 5. Right. So what I'll do, let's say given quota is of 3 units. So what I can do, I'll pick 6, and on picking 6 I'll try to convert 5 to 6. So I'll need one amount of value, so I'll just decrease 1 from here and I'll get 2. And since I converted to 6, I spent one amount. Again, to convert this to 6 I need 2 amount. So to convert this 6 I spend all of these 2 amount. So I got the maximum frequency equal to 3. Right. And again, if instead of 6, I will not go for 6. I'll pick 5 and try to convert all the lesser elements to 5. So to convert 4 to 5 I need amount 1. So again, if I spend 1, I left with 2, and 3 to 5 I need 2. So I spend this again. I got 3 as my maximum. So in this case, we'll only get maximum window equal to maximum frequency equal to 3. But it may happen for that the elements which are very close to each other, they'll give me some large number of very high frequency, but the elements which are very far away, they'll give me some high frequency, will give me some very less frequency, right? We can't convert large number into the given element which are very far away. So if this is how we want to proceed, then how would our algorithm look like? First of all, you will, if you think of brute force, we will start from I equal to n minus 1. So this is my given array nums. I start from I equal to n minus 1 and I'll go till I equal to 0. So whenever I am at index I, when I am at index I, so in my array, when I am at index I will traverse from right to left, from I till 0. For each I, I'll do that. I'll traverse from I to 0, and one by one I'll pick each element and try to make it equal to nums of I. So whatever value I'm having at I, I'll try to one by one match each value equal to that of I, by keeping in mind that I have this limited quota of k. So using that quota, I will try to convert I. When I run out of k, when k becomes 0 or less than 0, I'll stop and count, and I will count how many elements I have converted into I. So that will be my answer to that particular element. I do that for every single element in my array from right to left. And what will be the time complexity for that? N times we are traversing for each element, and in the worst case, around in first time I'll traverse n minus 1 elements, then n minus 2, then n minus 3, so on to n minus. So basically for ith index I'm getting, I'll traverse for n minus I elements. So on upper bound it will be of big of n square time complexity, right? But if we look at the constraints, we have the length of our array is 10 raised to power 5. So 10 raised to power 5, this gives us a signal that we can't use big of n square time complexity. 10 raised to power 5 means we are allowed to use n log n time complexity, right? So okay, this n we can use for iterating for the element which we take to convert rest of the elements into that, and to search for the elements which we want to make it equal to that fixed element, that we should do in log n time, right? That we should do in log n time. And since the array is sorted and the time complexity is want us to use the log n operation, so there is a high signal that we should use binary search. So we have to use binary search to do that. But how to use binary search to find out the number of elements which I can convert so that it become equal to nums of I? So if we look, we have some element here, A, B, C, D, E, F, G, H, I, let's say. So what I'm doing, let's say I have fixed this element I, and I want to convert as many elements as I can into this I, right? So first of all, I'll try to convert H to I. If I succeed, I'll go for G. If I succeed G to convert to I, then I go for F. If I succeed again, then I'll go for E. But if I fail at E, I'll stop, because there's no point of going the elements which are less than D, because they will definitely can't be converted into I, because they are even smaller. Will require more amount of K to convert them into I. So if I fail at E, then this means I have coverage till F, and this is the size of window I'm getting. So we are spreading a window, right? We are spreading a window in left side, right? So fixing I'll try to spread a window as far as I can. If I'm lucky, I will be able to convert every element equal to I, and my window will be something like this. I have converted every single element into I, and the window size will be equal to the size of the array. But if I'm not that lucky, I am somewhat less lucky, I may get I may convert element till b equal to I, so window size will be n minus 1. If I'm even less lucky, I may able to convert only these much elements equal to I. So on, if I'm not at all lucky, then I will not be able to convert any element, and I'm still at the same place I. So in that case, window size will be only 1. So in the worst case, I can have window size equal to 1, and in the best case, I can have window size equal to the size of my array, that is given n. And how to find the optimal window for each element? So we have to look for window for I, then we have to look for window h, window for g. So first of all, I will do this for in the element I, and search for the best window I can go for. Then I'll start for h, I look for best window for h, and for all the optimal windows for each element, whichever is the maximum in size, that will be my answer, because the window size is nothing but how many elements you have converted into the given element. So the most frequent answer will be the maximum of all of them. And one thing is that let's say I am able to transform these elements, these much elements into I. So what is the desired sum? What is the desired sum? Desired sum is that I want to convert h into I, g into I, f into I, and e into I. When e is converted into I, f is converted into I, what will be the desired sum? Desired sum will become whatever is the size of window times this value I, right? This value I. And what is the actual sum? Actual sum is e plus f plus g plus hi. Actual sum is e plus f plus g plus hi. So we want to increment this actual sum so that this window size will become equal to this much, window size times I, and I can only contribute k amount to this window, right? So what I need, take a window and add k to it. So if sum of window plus k, so if I'm adding k to the sum of current window, and that sum is greater than equal to desired sum, then that means that window is feasible, that window is possible. So let's say if I go for this window b, c, d, e, and f, g, h, and I, if I sum these values and if I add k, that is not equal to window size times I, or that is not greater than the desired sum. So our desired sum should be less than what we are getting from sum plus k, right? If our desired sum is less than whatever we are getting from sum plus k, then that window is feasible, and in that case we'll try to look for more bigger window, right? So we don't have to iterate every single element, I just want to find one starting point for that window. Ending point is fixed in each iteration. This is my ending point, and I have to look for a starting point. And to get the sum of the window, I can use the prefix sum technique. So I can prepare a prefix sum array. I can prepare a prefix sum array, and prefix sum array can help me finding the window size or window of any size in big O of one time. So I can find window size in big O of one time, and I can look for this starting point by using binary search. So this starting point will become my midpoint of so this start initially I'll start with low equal to 0 and high equal to this last element from which we are spreading the window. That will become a high point, and I look for the midpoint. So from mid to high I have the window. So I have a low index here, I have the high here, and I have a mid index here. So our window size is from mid to high, right? If this window size is feasible, I try to look for more bigger window. In that case, I will update high to mid -1, right? But if that window size is not feasible, I'll reduce the size of window. In that case, I'll just update low with mid +1. So these operations will take log n time in worst case, and we'll do this for every single element of my array. So for n elements, we are doing this search of window, and window search time is log n time. So overall time complexity will be big of n log n. Right. So if we let's try to code it. First of all, the step number 1, sort the array. So I have sorted it. Now by sorting, we have made sure that for each element, the lesser elements are present in the left of it, right of it, left of it, right? So once I sorted it, now I need to prepare the prefix sum, which will be able to compute the sum of my window in big O of 1 operation, in big O of 1 time. So first of all, I should get the size of my nums. So int n equal to nums dot size. Now let's prepare a prefix sum array. Which is again of size n, and let's initialize it with 0. And since we are summing the elements in prefix sum, so to avoid the overflow, I'm taking the type to long. So we know how to prepare the prefix sum. Nums 0 will become my sum at pre-sum 0. Then I'll go for rest of the indexes, i1, I less than, and I plus plus. Pre-sum I will be equal to nums of I plus pre of sum I minus 1. So after that I got my prefix sum. Now I have to search for the optimal window size for every single element starting from I equal to n minus 1 till I equal to 0, right? So let's do it for int I equal to n minus 1 and till I is greater than or equal to 0. I just decrement I. So my this I is nothing but ending index of my window. So I is ending window, and I will store the answer in this variable. Initially I'll kept it 0, and I'll keep on looking for optimal window size for each nums of I, and I will store the maximum window size in answer. So I'll get maximum of whatever the window size I have in answer till now, and I'll declare a separate function which is get get max window size, right? Get max window size. So that get max window size will accept this I index as parameter. It will take this pre-sum vector, and it will take this nums to get the value at that ending index, and it will also take the amount which we can spend, that is our quota, that is k, and this will give me the maximum window size corresponding to nums of I, and I keep on finding this window size for each element, and maximum one will be my answer, and in the end I can just return answer, right? So let's do it. The only thing we are left with is code this function of get max win size. So this first of all, this int I is nothing but end index and idx, right? And we have the vector of prefix sum, let's call it by reference that we don't prepare a copy, and we have original array vector, then our quota, that is k. Now initially my low value will be 0 and high will be equal to the ending index, so I just put end idx to equal to high, and we want to find the start index, which is of course the mid value, which is of course a mid idx between low and high, right? We want to find and we will store that starting index so that we can use later to return the answer. So when while low is less than equal to high, what you will do, first of all I'll find the mid index, right? So let's say mid idx is equal to while let's say it is only equal to low plus high by 2. This is my mid index. Now what is the desired sum, right? But first of all, what is the window size? What is the window size? So window size is from mid till ending index, so it will be end idx minus mid index plus 1. That will be the size from index I to j is nothing but j minus I plus 1, right? So the desired sum will be window size times nums of the value at end index, right? Now the sum will get by adding k in this current window. So how can I get the um, sum of this current window? For that we'll use this prefix sum, right? So to get the sum from index I to j, you just have to do prefix sum j minus of prefix sum I minus 1, and we have to handle that case when I is equal to 0, that is starting index is 0. So if mid is, so first of all let's declare int long sum plus k, sum of this window, actual sum of this window plus k, and if mid is equal to 0, that is mid is nothing but start of this window. If mid equal to 0, then I don't have to do pre-sum of and minus of pre-sum of start minus 1, because we are starting from 0 always to add in my prefix sum. So sum plus k will only be of pre-sum of and idx plus the amount of quota we are adding in it, k. If mid is not equal to 0, then sum plus k will be like this: sum plus k equal to pre size of sum of this window will be pre of sum and idx minus pre of sum, starting index is m, which is mid, right? Mid minus 1. So we'll discard the sum till mid minus 1. We'll accept the sum from mid to and idx, and of course we will add the quota k in it. Now if this desired sum is less than equal to sum we are actually getting, that is sum plus k, then we are good to go. We further try to increase window size, right? But before that we will store this starting point, the start of this window in this start variable. So I'll store mid in start and I look for more bigger window. For that I just have to update high equal to mid minus 1. If that is not so, if desired sum is not less than equal to sum plus k, then we should decrease our window size, and for that I should update low to mid plus 1. So once we are done with all of this iteration, start will have the starting index of most optimal window, and I can just simply return the size of this window by doing and idx minus of start plus 1. So this will do our job. It is accepted. And we are done.